Demis Hassabis, the head of Google DeepMind, proposed a benchmark for artificial general intelligence. He calls it the Einstein Test. It asks whether an AI trained exclusively on pre-1911 physics papers could independently derive general relativity, just as Albert Einstein did between 1905 and 1915. Many in Silicon Valley treat this as a problem of engineering and scale. Leaders like Sam Altman and Jensen Huang work from the premise that general intelligence is a byproduct of compute, an asset that accumulates as you feed more data into a single massive model. This diagram contrasts that model with a different thesis. On the left is intelligence as a stock hoarded inside one model. On the right is the Copernican correction, intelligence as a distributed flow across a verified, federated network. This chart highlights a specific empirical failure of the hoarding approach. It compares human baseline performance to a frontier model on the ARC-AC-AGI-3 benchmark, which measures fluid rule discovery. Humans score near 100%. The model scores 0.26%. That is a performance gap of 186 times. This gap suggests that the inability to crack fluid intelligence isn't a symptom of limited data. It is the result of a structural architectural flaw. Consider the greatest mathematician of the Roman Empire. Give them unlimited clay tablets, perfect motivation, and the entire Roman scholarly canon. Now ask them to perform differential calculus, to compute a limit as a quantity approaches zero. The calculation fails because Roman numerals lack a positional symbol for zero. There is no symbol to designate an empty column as a manipulable mathematical object. You cannot calculate what your notation cannot represent. This is the core problem for today's AI. Their underlying architecture is missing an analogous primitive, a first-class, addressable coordinate for verified epistemic absence. To find the exact failure point, we have to look at the terminal Softmax layer, the final step where a transformer model calculates the probabilities for its next output. Mathematically, this layer is identical to a Boltzmann distribution in physics. It distributes probability across a fixed state space. Every answer the model can give must exist somewhere on this predefined grid of known tokens. Consequently, the system has no coordinate to represent the state where a verified answer is missing. It cannot say, "I don't know," as an addressable mathematical fact. This is why AI struggles with innovation. The obscure features hypothesis distinguishes between type 1 discoveries, new relations between known ideas, and type 2 discoveries, which require an entirely new conceptual element. As this diagram shows, those missing concepts exist outside the model's fixed training distribution. When Alexander Fleming discovered penicillin, he had to recognize a biological anomaly, mold killing bacteria in a contaminated culture. He wasn't interpolating within existing knowledge. He was identifying a signal that had no prior address in the field of microbiology. Because current AI optimizes only within its fixed parameter space, it eventually hits a gradient horizon. It can refine its internal model, but it cannot breach the boundary to observe a reality it hasn't already been trained to see. The industry describes this process using tokens, a word borrowed from the semiotic theory of Charles Sanders Peirce. For Peirce, a token was never an isolated unit of data. It was the third leg of an irreducible triad. It required a sign, an object in the real world, and an interpretant, an agent whose actions are affected by that object. Modern AI architecture removed the object and the interpretant. It left only floating signs predicting other signs in a closed system. Without a connection to physical reality or an accountable observer, the system has no mechanism to verify its own claims. It is semiosis with its connections to the world amputated. The alternative is a notation inversion. The semiotic web architecture uses canonical concept identities and contextual token instances to stamp every relation with cryptographic provenance. This creates a semantic light cone of care. The blue cone is everything verified. The green is accountable action. The blank space outside is the semantic zero, an addressable mathematical state meaning no verified instance exists. When an AI hits this zero, it must trigger a structural bounded refusal. It stops the statistical guessing and instead seeks a new observation or queries a trusted peer. This architecture supports the reverse Einstein test. It recognizes that Einstein's intuition, the private insight of a mortal agent, was only the first layer of the discovery. His theory required a shared semantic layer of peers and a final real-world verification. That happened in 1919, when a solar eclipse expedition provided the physical evidence that transformed a coherent theory into corroborated knowledge. Intellectual breakthroughs only become knowledge when they are exposed to the friction of a world capable of proving them wrong. Scale maximalists seek to centralize intelligence inside a massive server farm, hoping that enough compute and data will eventually force a breakthrough discovery. They are sealing a model away from the world and waiting for it to autonomously derive new physical laws. But intelligence exists as a verified flow of discovery. It's the process by which a distributed system reduces the gap between what an agent knows and what the world requires. Mind cannot be separated from consequence. True intelligence is impossible without the capacity to act in the physical world and suffer the friction of being proven wrong.